This continues the lectures on Galilean relativity. In the previous portion of this lecture, I went through a one-dimensional example. In this lecture, we'll go through now two-dimensional examples, and for the two-dimensional examples that we'll examine, we'll keep it as simple as possible. When using the velocity transformation in the Galilean transformation, that is this expression right here, what we're going to do is just form a right triangle with the three vectors. We'll just take a look at two examples. Go ahead and begin to copy down the first of those two examples. Let me begin to read it to you here. Okay, a current moves downstream in a river at a speed of 2 meters per second with respect to the shore. A boat is capable of moving with respect to the water at a speed of 3 meters per second. And then part A of the problem is as follows. I have to move it here on my file. It says the boat is pointed directly across the stream. With what speed does the boat move with respect to the shore? You are already intuitively familiar with how this problem has to work, but usually the hardest part in a problem involving Galilean relativity is identifying everything. Okay, first of all, because we are once again talking about motion near the surface of the Earth, this then means that the stationary reference frame is the ground. In this case, in this context, it's the shore. So the stationary reference frame, O, is the shore, and then we have the moving reference frame and the object. We have the current, for example, in the boat. Which one is which? Well, the object is always the thing that is being described with respect to two other things. In this case, that's the boat. The boat's motion is being described with respect to the shore, and is being described with respect to the water. So right off the bat, the boat is the object, and then therefore the current, the river, that's the moving reference frame. So O prime is the current, and the object is the boat. Okay, let's picture a top view of the stream like so. So here's one shore, and here's the other, and then let's say that the current is flowing downstream like so with a speed relative to the shore at 2 meters per second. Right there, we're given the magnitude of one of the three vectors. Which one is it? Well, it's describing the speed of the current, O prime, with respect to the shore, O. So that's the magnitude of the velocity vector u. Okay, and then as I said, you're already intuitively familiar with how this has to work. So for example, let's say that the boat is pointed like so, as it says in part A of the problem, the boat is pointed directly across the stream. If we then have the velocity of the boat with respect to the water like so, plus the velocity of the water with respect to the shore, this then means that with respect to the shore, the boat is going to move like this, forming then the following vector triangle. We have here v prime plus u is equal to v. And we then therefore form a right triangle here on the diagram like so. Okay, now we are given the other side v prime of that triangle. It's given in the second sentence of the problem. In the second sentence of the problem, it says that the boat is capable of moving with respect to the water at a speed of 3 meters per second. That's describing the speed of the object with respect to the moving reference frame. That's the velocity vector v prime. So v prime is also given to us in the problem as 3 meters per second. Now to find the speed of the boat with respect to the shore, all that we have to do here is use a little bit of Pythagorean theorem to find the hypotenuse here of this right triangle. So the Pythagorean theorem here is going to be u squared plus v prime squared, and this then equals v squared. So now we just plug in the following. 2 squared, which is 4, plus 3 squared, which is 9. 4 plus 9 is 13, and then we take the square root. So ultimately, the speed of the boat with respect to the shore is just going to be the square root of 13 meters per second. So the square root of 13 is about 3.6 or so meters per second, like so. So once again, you're already familiar with how this has to work. We have the velocity of the boat with respect to the water, plus the velocity of the water with respect to the shore. That then gives us the velocity of the boat with respect to the shore, like so. Okay, now what we're going to do is take the velocity transformation here, multiply it by time to ultimately then end up with the position transformation in part B of the problem. Okay, let me read part B for us. I have to move my file once again. Okay, it now says if the stream is 100 meters across, how much time is necessary to reach the opposite shore? Okay, let me redraw the diagram here to illustrate. So here's part B. Okay, here are the two shorelines, like so. And then earlier from part A of the problem, we had the following velocity transformation vector triangle. So here was V prime plus U is equal to V. However, take the velocity triangle and multiply it by time. When you do, you end up with positions, like so. This vector here, this vector here, and then lastly, this vector here. Here in red is the position transformation expression, that is R is equal to R prime plus UT. Here's how these vectors work. This right here is the position of the boat relative to the water. Relative to the water, all that happens is that the boat just goes directly across the stream, like so. This is R prime, that's the width of the stream, that's what's given as 100 meters. And then this right here is the position of the boat relative to the shore. Relative to the shore, the boat ends up doing this like so as it crosses the stream. That's the position vector R, like so. And then lastly, the UT vector on this diagram is this vector right here. Basically think of this as the distance that the boat moves downstream as it's crossing the stream like so. This right here is the position of the water relative to the shore. This is UT. So we have then R prime plus UT is equal to R. So if you just take the blue vector triangle for the velocity and multiply it by time, that then gives you the position transformation expression. That gives you this red vector triangle. Now there's a couple of different ways to solve for whatever it is that we're looking for here in part B. It asks us to calculate the time necessary to reach the opposite shore. In order to do so, we're just going to take a look at this portion of the triangle, because this distance here, R prime, divided by the time necessary to cross the stream, that's equal to the speed right here of V prime. And now we just solve for t. So to solve for t, I'm just going to cross multiply here a little bit. The time t is equal to R prime over V prime. So this is 100 meters divided by 3 meters per second. So 100 divided by 3 is 33 1/3, 33.3 seconds. That's how much time is necessary for the boat to cross the stream. Okay, now I've posted for you a screencast in today's folder that in part shows this problem. It's called Vector Addition, the Velocity of a Boat. Before you watch that screencast, however, there are a couple of extra parts that are shown in that screencast for some of the more advanced classes. But part A of this problem, showing the right triangle, is depicted very nicely in that screencast. Go ahead and watch that screencast now and then come back to this lecture. Okay, now that you've watched that screencast and you were able to see the triangle itself in the film, let's now move on to the second and last example here for Galilean relativity. Let me introduce this example to you in the following way. It involves the rain. So let's say, for example, that you're standing stationary on the ground and you look at rain falling vertically at a constant speed. Now, if the rain falls at a constant speed, what that means is that air resistance is involved. The rain is not in free fall, it's not accelerating. And then let's say that you get into a car and you then drive into the rain. And then as you drive into the rain, you may be saying to yourself, wow, it's really raining hard. Whereas earlier, when I was just standing on the ground, it didn't seem to be raining hard at all. Why is that? Well, if you've ever wondered why that is, the reason for it is because you're actually seeing the magnitude of different velocity vectors. Okay, let me go ahead and erase the board behind me, and then I'll introduce that problem here on my screen in just a moment. So let me do some erasing. Okay, I have to move my file as well. Okay, it says rain is falling vertically at a constant speed of 8 meters per second. There is air resistance, as seen by a stationary observer. A second observer is driving a car that is moving horizontally at a constant speed of 30 meters per second with respect to the ground. Hang on a moment. It then says, with what speed does the driver see the rain falling? Okay, the hardest part of this problem is just picturing the vector triangle. Like in the last example, however, we're given two of the vectors and we have to find a third. So let's go ahead and begin by defining things. All right, so once again, the stationary reference frame is the ground, as it always is. But then we have the moving reference frame and we have the object. We have the car and the rain. Which one is which? Which is the object and which is the moving reference frame? Remember that the object is always the thing that is being described with respect to two other things. In this case, it's the rain. The rain is being described with respect to the ground and with respect to an observer in the car. So then therefore the rain is the object and the car is the moving reference frame, O prime. Like so. Okay, and then it says that the rain is falling vertically as seen by a stationary observer with a constant speed of 8 meters per second. That's describing the magnitude, once again, of one of the following vectors. Is describing the speed of the rain, the object, with respect to the stationary reference frame O. So it's describing the magnitude of V. The V vector points straight down like so, with a magnitude of 8 meters per second. Okay, and then we have the moving reference frame, the car, will say moving in that direction relative to the ground at 30 meters per second. That's describing the speed of the car, the moving reference frame, with respect to the ground, the stationary reference frame. So that's the magnitude of the vector U. Like so. Okay, and then the unknown in all of this, forming the vector triangle, is going to be the V prime. The V prime is going to describe the velocity of the object, the rain, with respect to the car. So what does that then therefore look like? Well, picture it in the following way. Draw upon your own experience at looking at the rain while you're in a car. So if you're stationary on the ground and the rain is falling vertically like so, and then you get into a car and then drive in this direction through the rain, roughly how do you see the rain as falling? Well, you see the rain as falling while you're in the car like this, like so. So then therefore the velocity of the rain relative to the car, V prime, is going to look something like this. And then here's how we form the vector triangle using the tail to tip method, the vector addition. We have the velocity of the rain relative to the car plus the velocity of the car relative to the ground equals then the velocity of the rain relative to the ground like so. So V prime plus U is equal to V. And then what we'll do is once again use a little bit of Pythagorean theorem here to figure out what V prime is. We once again form a right triangle in this example. Now this side of the triangle is 8 meters per second. This side of the triangle is 30 meters per second. And now we just use a little bit of Pythagorean theorem here to find V prime. So V squared plus U squared is equal to V prime squared. And now I just plug in. So first of all, I have V squared, so 8 squared is 64, plus then 30 squared, so 900. Take the square root of all of that. And it ends up being quite a large speed in this case. V prime is equal to 31 meters per second. So to summarize, when you're just standing on the ground, you see the rain at this. However, when you're in a car, you see the rain at this. Notice how much larger this speed is than this speed here. So if you've ever been in a car while it's raining and you've said to yourself, wow, it's really raining hard, well, it's because you're seeing this velocity vector here, whereas if you were just standing on the ground, you'd be seeing this velocity vector here. Normally, I demonstrate this to my students in the following way. Let's say, for example, that sometime later in the year, it's raining, okay, assuming that it ever rains again. Well, if it just so happens to be raining while class is going on, what we do is pause and go outside to the balcony just outside my classroom door. And then assuming that there's no wind, you look at the rain and it's falling vertically like so. And then what you do is you run down the hallway in this direction and you look at the rain as you're doing so. And you see the rain very noticeably falling on a slant like so. You can see the V prime vector itself like this. Okay, this concludes the lectures on Galilean relativity. This also concludes this unit on vectors and kinematics.